Hey everyone, so there's one last thing that I need to talk about when it comes to energy, and that's this idea of spring energy. Now, for the most part, we've already covered the majority of energy. It's the conservation of energy, that's actually the tough one. What I wanted to do though is just add in one more type of energy into the mix. Now, the reason I didn't include this earlier before I did conservation of energy is mainly just because most of the conservation of energy problems you'll see will typically deal with gravitational potential and kinetic, that relationship, also with work and heat. Spring energy doesn't really come in too much, compared to the other ones. So that's why I kind of like left it off here. I wanted to first just start going over the idea of conservation, focusing only on the main energies, and then we'll add in this next one at the end. Now, this is, I call this spring energy. It's more akin to elastic energy. I probably should be calling it that. But basically, the idea is that it's the energy stored in rubber bands. I mentioned before that there are multiple different types of potential energies. There's gravitational potential energy. There's the chemical potential energy, electrical potential energy, things like that. So there are other ways that we could store energy in a bunch of different ways. And it turns out that elastic energy, storing energy within rubber bands and of springs, is another type of potential energy that we can deal with. So just like how we have the gravitational potential energy related to height, where if we lift an object up and we drop it, that potential turns into kinetic, the same thing's going to apply when it comes to spring energy. If I take a spring and I either compress it, get it closer together, or I elongate it, that's going to store some energy into it. And we call that stored energy spring potential energy or elastic potential energy. And it's represented by US. Now, I should clarify that this is true for any springy object. So, rubber bands also have this spring potential energy. Don't think that it just has to be a coiled spring. Now, one question that you could ask yourself is what are some factors that could affect how much energy is stored in the spring? Well, one thing that you could think of is the amount that it's compressed or elongated. If you take a rubber band and you pull it back a little bit and you let go, it's going to go some distance. But if you pull back further, two, maybe three times further, it's going to end up traveling a lot farther than it did before. So the more you pull that rubber band back, the more kinetic energy it ends up gaining after you release it. Or if you were to flick it at someone, they would feel more energy, more pain when it hit them because of the amount of energy you gave it by making it stretch longer. So, how much it stretches is one of the factors. Now, another factor that you could think of is how rigid the spring is. Now, we haven't really talked about springs too much before, so I'm just going to throw it in there in a moment. But there is a characteristic of springs that refers to the how easy or how hard it is to stretch it and compress it to basically like whether or not it's elastic or not. So a spring that has a very high rigidness, let's say, may end up storing a lot more energy than something that's fairly loose and easy to stretch out. Now, we actually call that rigidness of that spring the spring constant, and that's represented by the symbol K. So the spring constant is referring to how hard it is to actually stretch out that spring. The higher the spring constant, the harder it is to pull apart. A good example of this is your bed springs. In a bed, the springs in your bed are fairly rigid. It takes a decent amount of force for them to compress a bit. Compare that to a slinky that is very easy and pretty much will elongate through its own weight. That would have something like a very low spring constant. So that's what we mean when we say the rigidness of the spring. Now, in the equation that we're going to end up finding, the displacement, how much it is either compressed or elongated, is represented by the symbol x. Now, as far as we're concerned, there is no difference between it being compressed or elongated. You stretch the spring out 5 centimeters, you compress it 5 centimeters, it ends up being the same thing. So don't overthink it. Compressing and elongating basically means nothing. Now, the spring constant is going to be measured in newtons per meter, and the displacement is measured into meters. Now, the next question that we want to know is, well, how much energy is stored in the spring? Now, I'm going to quickly show the derivation of how we do this before I show the equation because I think the derivation's interesting. Now, if you recall, one of the things I had mentioned was that the equation that we got for gravitational potential energy, the MGH, came from the fact of saying that, well, there's the work being done, which by gravity, is the force due to gravity times the distance, vertical distance that it's lifted up. We could replace Fg with mg and d with h, and we get mgh. So we took the equation for force and reworked it to talk about gravity. We could do something similar for elastic energy. The issue is that the force isn't the same as gravity. With gravity, the force stayed the same when you lift it up, but with elastic energy, it turns out the force changes as we compress and elongate the spring. Now, this was an equation I didn't show you before, but on the reference table, you have this equation, F equals kx. It's actually written with these absolute value bars on your reference table. Don't overthink them. Remember, the absolute value bars are just to tell you that those two are not in the same direction. But what matters is that there is this direct relationship between force and compression and displacement. Now, with this graph, I can use this to figure out work. So, if you recall, when we have a graph, we have to either do area or slope. It turns out that if I have a graph of force versus distance, if I want to find the area, if I want to find the work, I need to find the area underneath the line. So this shape is a triangle. So the work is going to be the area of the triangle, which is half base times height. My base is x, my height is f. Now, this is a equation for the spring energy, but it's not the main one that we're going to be referring to. Because what we can do is go back to our original equation and say that, well, force is equal to kx. So that's 1/2 x times kx. We have two x's here, and we end up getting this equation, 1/2 kx squared. And this actually ends up being the equation that we're going to use for spring potential energy. All right, so I'm going to erase all this. So this is the equation that we have for the amount of energy stored in the spring. And I want to show where the equation comes from. That this equation doesn't just come out of the ether. It doesn't just, someone say that's what it is and that's what it'll be. It's coming from our definition of work. That work is this, relationship between force and distance. That if we took the area of the force that we plot, we end up getting the work being done by the system. So this is essentially our equation, and what we're going to do is plug numbers in, chug out our answers, and that's it. Like I said, we'll do one question where we do a practice using this equation, and then we'll see how this equation works in a conservation of energy setup. All right. Like I said, the x value is, it's important to note that the value for x, it's the change in the spring's length, not the actual length of the spring. So you have to have the reference point of where was the spring unstretched, or where would it normally be when it's at rest. And then x is going to be how much it elongates or compresses from that initial point. So here's the first question. So pause the video, work stuff, and we'll go in a second. All right, so they want the potential energy stored in the spring. So I take my equation, plug my numbers in, and I get my answer of 62.5 joules. Easy enough. All right, now let's actually see how this works in a conservation energy setup. So here's the next question. Pause the video, work itself, and we'll go in a second. All right, now remember, the way that we end up wanting to approach conservation energy problems is we want to find 2 points and identify all the energies that are acting at those locations. Now, if I look at this point is raised to some height. So it's going to have some gravitational potential energy and some spring potential energy because there it is being pushed against the spring. And it's going to end up going to H2. And it says that it just reaches the top of H2. So this also has potential energy. Now remember, one of the key things that I can do with potential is I can set ground level. I can set zero, my reference point, wherever I want. So because even though this has these other locations that are lower than H1, I don't care about them right now. So I'm going to pretend that this is the ground and that all this is actually junk. At this point, I no longer have gravitational potential. I'm going to have spring potential. Now up here, because it says it just reaches the top, that means it's getting here with a speed of 0. So there's no kinetic energy here. All that I have here is gravitational potential. So I'm going to set the spring potential here equal to the gravitational potential there. Use the equations 1 half kx squared equal to mgh. And when I plug my numbers in, I want to make sure that the h that I put in is the difference in these heights. Because remember, technically, this UG has an implicit delta in front of the U and the H that I tend to drop just because I'm a little lazy. And you technically don't need it as long as you remember that the height is always a change in the height, not necessarily what it actually is relative to the ground. So H1 is 5 meters and H2 is 10 meters. So the difference in the height is going to be 5 meters altogether. So when I plug this in and solve for x, I end up getting 3.16 meters. Now here's the really nice thing. If you didn't like the way I just did this, what you could have done was, oops, what you could have done was actually did UG plus US, where you actually do take into account the height relative to the ground. Then up here, you'd have UG. And you would find that you'd still get the same answer when you set it up. You'd have UG plus US equals to UG, this being at position 1 and this being at position 2. When you do the MGH here, the H here would be 5. Then we'd have this US. And then over here, the H would be 10. And when you move this over, you'd end up with 10 minus 5, which is 5. So, like I said, you still get to the same answer as long as you set it up properly. It doesn't really matter which way you want to do it. If you want to set the height, like take into account its actual height, that's fine. Just be consistent. Make sure that if you're doing it for this object, measuring it to the ground, you do it to every single object or every single point afterwards. All right, now for part B, it says it wants to know what the speed is at this location. Now, this is the nice thing about doing this with conservation of energy is that it doesn't matter which points I set equal to each other because conservation of energy says that they're the same. Based off of what I wrote here, I have UG plus US at this point. I have UG at this point, and then down here I'm going to have some potential and some kinetic. According to conservation of energy, I know that these three are all equal. So if I want to figure out the speed at this point, I need to figure out the kinetic energy, and I can get that by either setting it equal, this total energy equal to this energy, or I could set this equal to the initial energy. It really doesn't matter. It's, again, whatever floats your boat. What I'm going to do is I'm actually going to set these 2 points equal to each other, mainly because I like to try to simplify my problems as much as possible, and I have one energy equals to 2 energies. I'm also actually going to do a similar trick that I did last time where I set this to be my 0 point. Because again, I'm redoing the problem and I don't really care about everything else. So I'm making this 0, and that means that this potential that was on the H3 side is now 0. So I'm not taking that into account. And now I'm going to look at the change in height between these 2 points and set that equal to the kinetic. So when I do this, H2 is 10 meters, H3 is 2.5 meters, that change in height is going to be 7.5 meters instead. Use this, solve for V, and I get 12.2 meters per second. Again, if you didn't want to do it that way, you would have still gotten the same answer if you did UG with 10 meters and equal to UG plus K, where the H is 2.5 meters. You could have set it equal to this, equal to that. It's fine. It doesn't, as long as you're setting the energies properly, you'll still get the same answer. And that's, again, the beauty of conservation of energy. All right. Now, here's a follow up to that. So, pause the video, work itself. I'm going to go over in a second. Now, this question may seem like it requires calculations, but it really doesn't. What you can do is take advantage of the idea of conservation of energy, and remember that when we have these boxes, the AP will do this for a specific reason, and that is to make sure that we have our proportions set up properly. So in this case, I need to make sure that not only do I draw in how many boxes, like what energies I have at each point, but how many boxes it goes up has to be consistent throughout this problem. So what I want to do is I want to start at a point where we only have one type of energy, and the only point that that occurs is at H2. H2 was at the very top of the hill where it only had potential energy. So that means all my energy is going to be stored in gravitational potential. So I'm going to make a bar on UG that goes up 4 boxes. And you'll see why I'm doing 4 in a second. Now I need to go to this initial parts. So we have H1 compressed and H1 released. This is referring to the spring being compressed. And then this is referring to when the spring finally releases, but the block hasn't yet gotten to the point where it's going up the hill. So it's still at H1. It's just two different points of that spring releasing. So if I look at this first case, and I look at the energies that I have at H1, I do have gravitational potential, and I have spring potential. Uh, I can calculate what my gravitational potential is, and I can scale it that way, or I can realize that the height at H1 was half the height of H2. And because gravitational potential has a direct relationship with height, I know that if the height is halved, then the potential energy is halved. So if this is 4 boxes, this has to go up 2 boxes. Now, the important thing to keep track of is that conservation of energy has to hold true. Over here, I don't know how much energy each box is, but over here I drew 4 boxes in total. So every single section should have 4 boxes. This has only 2 boxes, so there's 2 more boxes left. I already noticed that it had to be spring potential, so that means that there should be 2 more boxes of energies in the spring potential. If I go to the next part at H1 released, well, the height didn't change, so my gravitational potential should stay the same. But now that the spring's released, it no longer has that spring potential energy. So where is that energy going? Well, there's only one other type of energy that it could be, and that's kinetic. So the flow of energy, that all that spring potential got converted completely into kinetic when it was at H1. Then that kinetic, as it goes up, turns into gravitational potential, adding on to what I started with to go a little bit higher. And now I get to H3. H3 goes a little bit lower. And if we recall, H3 was half the height of H1. Since H1 is 2 boxes, and because height has that direct relationship with potential, this has to be half of that energy, which is 1 box. Once again, conservation has to hold. So in total, I have 4 boxes. That means I have 3 more boxes to spare. There's no spring at H3. So all 3 boxes go into the form of kinetic. And now this is what my bar chart will look like. All right. Let's do the next one. Pause the video, work itself. I'm going to go over in a second. All right. So this one's going to be a little bit trickier. Uh, Mostly for part A. Part B won't be as tricky. So, just like last time, it actually really helps to to draw a picture in order to identify the energies. So, they say here that my spring is normally like this. I don't know how long it is, but it doesn't matter. I'm compressing it 10 centimeters. So this gets compressed 10 centimeters. And when I release it, it results in it going up 50 centimeters from where it started, from this point. So the question is, what is the spring constant in the pogo stick? Well, in this part, we have the spring being compressed, so I have spring potential. When is at this point, I have gravitational potential because the spring has finally released. So I know that those two energies are going to be equal, and I can set their equations equal. Now, this is where it gets a little tricky because what numbers we plug in matter. I'm looking for K, so I'm going to leave that blank. X is how much the spring gets compressed. That one's actually really easy. It gets compressed 10 centimeters. So I'm going to make sure that I plug in zero point 0.1 for X, to keep it in the proper units of meters. M's easy because that's just 80 kilograms. G's easy, that's 10. H is where it gets a little tricky. This point is referring to this location here with the spring being fully compressed. MGH is being referred to the maximum height when it's at this location. The height has to be taken from my initial point, how high I am from where I started this spring energy. The 50 centimeters is from the unstretched spring or the uncompressed spring. So I have to actually take the 50 centimeters and add in the compressed 10 centimeters to get zero point 0.6 meters. That's actually the big thing that is tricky. In this specific case, because those distances are really close together, it matters. I've seen a lot of problems where you can actually ignore how much the spring is compressed, mainly because it goes very high up into the air. So it ends up being very negligible that it got compressed an extra 10 centimeters when the max height is somewhere like 10 meters. But in this case, because they're really close together in magnitude, I do have to take that into account. Unfortunately, my picture is actually really poor, so it's hard to see, but it's important to note that I'm taking it from the height uh, where it's being compressed to where its maximum height is. So 50 plus 10 is 60. So I end up getting a spring constant that's 96,000 newtons per meter. All right. Next one's a little bit easier depending on how you set it up. So pause video, work self. I'm going to set. Oh, actually, we already went over this one. So now we have to figure out what the velocity is. The easiest one to do. So if I actually draw this out, the way it sets up is like this. At here, I have spring potential. It releases the spring releases itself to lift it up a little bit in the air. So I technically have a little bit of gravitational plus some kinetic when I'm comparing it to this beginning height, and then it's going to end up reaching this point, which is 50 centimeters in the air, which has straight potential. What I can do to make my life easy is set these 2 points equal to each other and ignore the 10 centimeter height here because everything is going to be taken from this same point. Again, ignore everything from the bottom. This is now my ground level because that's how I'm setting up my problem. So I can set the kinetic energy from right when the spring was released equal to the potential energy where I'm taking it from the spring being released to the maximum height. Plug my numbers in. I'm dropping the mass in here because there's a mass on both sides. So this M and this M drop. And I'm going to put 0.5 meters here because, again, I'm taking it from after the spring has been released. The 0.6 was when the spring was still being compressed. So I'm going to leave it as 0.5. And I'm going to get that it's 3.16 meters per second. Now, if you wanted to double check, you can set the spring potential here equal to UG plus K, where the height is zero point 0.1 meters and the compression is also 0.1 meters. and you would find that you get the exact same answer. All right, here's the last one that we're going to do. Pause the video and work on yourself, and we'll go over in a second. All right, so this one's a little bit trickier. They wanted us to figure out the speed of the block just before it hits the spring. So when I do this, again, it's going to this location. At this point, it's got potential, and at this point, it's going to have straight kinetic. Again, I know that it's technically at still some height, but I'm cutting it here, ignoring everything below. I'm treating this as my zero potential point. So I set my potential energy at this location equal to the kinetic here. The only thing that I have to be careful of is UG requires H. So what I can do is make this triangle. Actually, let me redraw the triangle over here. If the hypotenuse of my triangle is 6 and this angle is 30, then the height is going to be 6 times sine of 30. So when I set the energies equal to each other, I have to put 6 sine 30 in for H. Again, my masses drop out because I just have, these potential equal to kinetic. And I end up getting 7.75 meters per second. Right? And then for part B, it wants us to figure out the spring constant when it gets compressed. Once again, what I can do is, now that it's fully compressed, I look at the energies. It's got potential here and spring potential over here. The one thing that I have to be careful of is now that the spring got compressed 3 extra meters, I have to add that into my new height. Because again, I'm looking at the height not just at any location, but between the two specific points I'm looking at. So I'm looking at from where it starts to when the spring is fully compressed. So instead of it being 6 meters, now it's going to be 9 meters along the incline. And I do the same thing where I make my little triangle. H is going to be 9 sine of 30 this time. So when I set the energies equal to each other, I make sure to include that in for the H. Notice I am not dropping the mass this time because there is not a mass on the spring potential side. I put in the 3 because that is along the incline. I don't that's how much the spring compresses. It doesn't matter if it's on an angle or not. So that ends up being 3. Plug my numbers in, and I end up getting that the spring constant is 200 newtons per meter. And that's it. There's going to be a follow-up video where I just go over some conceptual questions, but that's pretty much it for the elastic energy and for this, energy as a unit. Again, you just need to be able to recognize the equation for elastic energy when we have it, and then just incorporate that into the same process that we do when it comes to conservation energy, where we ask ourselves, what energies do we have, what energies are equal, yada, yada, yada. So if you have any follow-up questions, feel free to let me know. Otherwise, good luck and have a great day.